Long part 2. Using this formula, A, the amount after a certain amount of time, P, that's your initial investment, interest rate, number of times it compounds in a year, and time. So, gives you P is 12,500, that's this. So the amount, 12,500 times 1 plus, now the rate is 6.5. We've got to move the decimal 2 places to the left. So it's 0.065. And that is over N, which is number of times it compounds per year. Semi-annually means twice. So that's over 2. And that's to the N, 2. And then number of years, 10 years. That's that T times 10. So this turns into 12,500 times, let's just calculate this. Here we go. 0.065 divided by 2 plus 1.0325. So 1.0325, 2 times 10 is 20, so we got to figure that out. So we're going to take our calculator, and here we go. 1.0325 raised to the 20th power. We're going to multiply that by 12,500, and that is $23,697.97. So, almost doubled your money there. Seems like a good deal. Okay, now we have a different formula given whenever a problem is given to us where it compounds continuously. Very similar to this, but now we got this letter E involved in the formula. So the amount that it's worth after time, initial investment is $2,000, not as much thrown down initially. And then that's E, so I'm just going to write it in here, E. Remember that's 2.71. And the rate is 1.7, so we're going to expand that to 0.017, so that's 0.017 times T, 8 years. So now we got to do the math here. So 8, am I on the screen here? I'll try to do it right here. There we go. So 8 times 0.017 is 0.136. So we got to go 2.71 raised to the 0.136 power, and that's 1.145. And we're going to multiply that by 2,000. And we get approximately $2,290.41. So there you go. So this problem, I'm going to give you a little wink, wink, nudge, nudge, is difficult enough to where I qualify it as a potential bonus problem. But that doesn't mean it's impossible to do. And we did not talk about this during the unit. So here we go. The graph of an exponential model in the form y equals, there's our generic equation of an exponential function, passes through the points, x is 3, y is 5, and x is 4, y is 10. What are we going to do with that? Well, we're going to build two equations. Number one, we're going to use this, plug it into here, so y equals a times b to the x power, and equation number 2, we're going to use this information, y equals a times b to the x power, which is 4. Now we're going to solve for a. You see these a's sitting all by themselves? We're going to solve for it. Divide by b cubed, divide by b cubed. So we get a is 5 over b cubed. Now why are we doing that? Watch this. So now I'm going to solve for a over here. Divide by b to the 4th, gone. Divide by b to the 4th, spin it around, a equals 10 over b to the fourth. Now if a equals this stuff and a equals this stuff, doesn't that mean that this stuff has to equal that stuff? So I'm going to show that by going 5 over b cubed equals 10 over b to the fourth. Now I'm trying to solve for b. So I'm going to multiply both sides by b to the fourth, because that would cancel this. Multiply that side by b to the fourth. Now notice, b to the fourth over b cubed would just be b to the first. They'd cancel, and I'd be left with b. So 5b equals 10. Now if I divide by 5, I get b is 2. So I'm going to go to my piece of paper now, and I'm going to take this problem, well, actually I don't want to get rid of that yet. So remember, b is 2. So I need to still find a, and I'm going to do that by popping it in either one of these. But because this is simpler, I'm going to go 5 over 2, that's b, cubed, which is 5/8. I'd get the same thing if I put in 2 here. But let's stick with this. Now I can take this and say, aha, now I know my equations. Y equals a, which is 5/8, times b, which is 2, to the x power. Now let's pause that a second. Now just so I don't chew up all your video time, I know this is my correct answer. And I'm going to show you what you'd need to do to this, this, and this, and this, until you find something that's true. But rather than chew up your whole video time, I'm going to show you how the right answer works. So once I got to here, and I know this is my formula, I know x is 5, and I know y is 20. Now if I plug it in there, I'd get 5/8, y equals 5/8 times 2 to the x power. So if I put 20 in for y, and then I put 5 in for x, do the math, 20 equals 5/8, make sure I'm on the screen there, times, what is 2 to the fifth? Well, 2 times 2 times 2 times 2 times 2, 4, 8, 16, 32. And if I go 8 goes into 32 4 times, 5 times 4 is 20, and look what I get. I get a true sentence. And that's the only one where I'd get a true sentence. But if I plug that x in and that y in, I'd get a false sentence. Let me just show you that one. So y from here equals 5/8 times 2 to the second power. You can already see that 0 does not equal this stuff, no matter what it is. So that would cancel. And you'd get a false sentence there and a false sentence there by plugging things in. This is the only one that's true. Now you can see why that might be a bonus problem instead of a normal problem. All right, life gets a little simpler now. Evaluate, which means solve each logarithmic expression. Well, remember, there's always 3 parts, and that's the part that's missing. This is my base, that's my exponent, that's my answer. So this problem's basically saying, solve that. Well, some of you would just go common sense, and you'd just keep going 3 times 3 until you get 81. 3 times 3 is 9, 9 times 3 is 27, times 3 is 81. So you'd say, x is 4, because 3 to the 4th power is 81. But what I want to remind you of is common bases, happy places. So I'd rewrite this as 3 to the x equals, I know I could rewrite that as 3 to the 4th, and then these would cancel, and x would have to equal 4. Different way of looking at it. This one, again, we're missing that thing, that third part. What is that third part? Well, there's my base, there's my exponent, so it's 8 to the x equals, and here's my answer, 1 over 64. Now, nothing's jumping out at me like this one where I could just use common sense. So I got to resort to common bases, happy places. Now remember, I said, look at these two numbers. Which one's bigger? Clearly 64 is. So is there a way I could rewrite 64 with a base 8? And the answer is yes, 8 squared. Now the next thing I'm going to say is, remember the rule, if I put a negative exponent If I take a negative exponent and put it where it ain't, it becomes positive. But what if I put a positive exponent where it ain't? It becomes negative. So I'm going to bring that up, and I'm going to get 8 to the negative 2 power. Now that I got common bases, they drop out, so I can see that x equals negative 2. There's my answer for number 11. Number 12. Same thing. Put that x in there, start with the base, go to the exponent, so 4 to the x equals whatever that is, negative 4. Now you got to use some common sense. There is no way I could raise 4 to any power and get a negative answer. So this is no solution, just using some common sense. This is similar to the stuff we were doing, but they're not logarithms, they're just equations. But the same thing holds true like here, common bases, happy places. So here's a base, here's a base. Which number is bigger? The 27. Is there a way I can rewrite that 27 as a base 3? And the answer is yes. 3 cubed. Just like we did over here. Now we're going to take this, bring it up. So we'd get 3 to the negative 3rd power. The common bases, once we've achieved them, now we know that this exponent has to equal that exponent. So 2x equals negative 3, divide by 2, divide by 2. X is negative 3 halves. And there you have it. Let's keep going. This one, common bases, happy places. No, it's not going to work. Look at, that's just crazy talk. So this is where we slap a log on this side. We slap a log on this side. And now, remember what we can do. We can actually take our calculator and turn these into actual numbers. So we're going to go log of 4.7. That's 0.672. So 0.672. Now this log of 236 is 2.37, we'll call it. But we're going to take advantage of law 3, which allows us to take an exponent and put it in the front. So it's x times whatever we got when we typed it in our calculator, which is right here, 2.37. So 2.37. I got to solve for x. So divide by 2.37, gone. Divide by 2.37. So now, here we go, 0.672 divided by 2.37, I get 0.283. So x equals 0.283. No way you can solve that without logs. Very similar to this. But remember, when you see an e as the base, you don't slap an log log, you slap a natural log on there. And now we got x minus 1 to the power. Slap a natural log on this side. Now we got to do a few things. Now we're going to use the natural log button. Natural log 14.9. That's 2.7. We're going to round a little bit. Now notice we can bring our exponent in the front and we're trying to solve for x. Remember what natural log of e is. That's an automatic 1. So remember, if we had that problem over to the side, there's an invisible e here. We'd figure out what this is. Well, e to the first power equals e, so e to the first is e. X has to be 1. Bottom line is, we bring x minus 1 in the front. We know this actually cancels, or it's actually times 1, so it doesn't change it. We get 2.7. Add 1 to this side. We get x is 3.7. Stick a fork in it. Okay, number 16 says, for number 16 through 18, sketch the graph and sketch the graph of its inverse. Remember, the trick is, we got to remember, it's going to reflect over the line y equals x. So with all that being said, what does this even look like? Well, if you recall, this is equal to y, so if I spin this thing around, and I think of it like this, and I turn it into an exponential equation, it would be base exponent equals my answer. So, if I let y equals 0 on this problem, you can see that anything to the 0 power is 1. So I would have this little chart, and strangely, because that's my y, I'm going to start with my y, stick it in here, and I would find that x equals 1. And remember in class, that's always our locator point. For this 2 could be a 3, 4, 5, 6, 7, doesn't matter. All our locator points are going to be 1, 0. We emphasize that in class a lot. And then we recall that it looks something like this. Now, I'm not being perfect here, but that's generally what it looks like. It's probably a little flatter, but... So, the locator point is definitely 1, 0. That's what we just found. Explain with words what you did to this point to assist in getting the graph of the inverse. Well, remember, the inverse takes all my x's and y's and flips them. So I know one of my points is going to be 0, 1. Now that is helpful because, remember, y equals x goes just like this. And essentially, we're going to reflect this guy right over that y equals x line. And so I'm just going to try my best to duplicate it. And it would be something like, all right, so this approaches the y-axis, so if it flipped over this, it would jump right up into this area, and it would look like this. So there it is. This right here is the graph of the inverse function. Okay, so we go here. This should be easier. I think we're going to stop that. We're going to call that the end of part 2.